Hello everyone, this is Dr. Sirisha, working as Associate Professor in Institute of Aeronautical Engineering College. Today we are going to discuss about traversal techniques in graphs. So what do you mean by graph traversal is the primary concern question over here. So the graph traversal is a technique where we are going to search for a path to traverse between all the nodes, touching each and every node only once, is nothing but traversals. So traversals is also used to decide the order of vertices visited in the same process, right? So basically there are two different types of graph traversal techniques. One is depth first traversal and the other is breadth first traversal technique. Let's understand these two techniques in this session. Let's start with depth first search, that is also known as depth first traversal technique. Here we are going to visit the adjacent unvisited vertices starting from an initial vertex, even also known as a node. We generally call nodes, referred to the stations or the places when we draw a graph, we call them as nodes, even though these nodes are referred as vertices also, right? So let's start with a source node from where we want to start our traveling. That will be the first visited node or the visited vertex. So mark it as visited and display it. Here to perform depth first traversal, we are going to use stacks. Stacks are going to be a helping hand for us to perform depth first traversal. So once a node is visited, it will be pushed into the stack. So step 2. If no adjacent vertex is found, which is unvisited, pop out from the stack a vertex and repeat the same process that we are going to do. Search for an adjacent unvisited vertex. That is step 1. Step 3. Repeat these steps 1 and 2 until the stack gets empty. Let me explain you with an example. Have a look at this graph. This graph is having 6 vertices. Initially, all the 6 vertices are unvisited, right? And I'm taking an empty stack. In an empty stack, the top of the stack default value will be -1, and in the output it is showing null. With the just hyphen I have shown, problematic way it will be a null value, nothing. It is an empty one because I have not visited any node yet, right? I'm going to start it with a node A. Let's start with A. So I have differentiated with the color red. So as A is a visited node, so A is pushed into the stack as well as sent to the output. As you can see, in A is being sent to the output as well as pushed into the stack. Now top is going to point the first value which is inserted into the stack, which is A, right? So who are all the unvisited neighbors of A? You can see B and C are the 2 unvisited neighbors of A. Choose one of them. I have chosen B. So as I have traveled from A to B, so now B is the current node I'm talking about, right? And it is being visited and pushed into the stack. As it is visited, I'm going to send that to output. See, you can see now the visited nodes are A and B, right? So as I told you, stack is going to be a helping hand for us in this process. Now, the current node which is on top of the stack is B. In B's point of view, who are all the neighbors of B? Actually, the neighbors of B are A and D and E. All the 3 are neighbors of B. but our point of concentration is only the unvisited neighbors of B. A is already been visited, so the unvisited neighbors of B will be D and E. Choose one of them to traverse, right? So I have chosen D. As D is the current node which is pushed into the stack, as it is a visited node, I am going to send it to the output, right? So on top of the stack is now D. Who are all the neighbors of D? Coming to the neighbors of D, B, E, F are the neighbors of D. But point of concentration is the unvisited neighbors of D. B is already been visited. So now we have only E and F in our hands. Choose one of them to continue your depth first search and send it or push it into the stack and mark it as a visited node, right? So I have chosen E and I have pushed it into the stack. Fair enough. Now on top, as E is already been visited, I have sent it to the output list which is a collection of visited nodes. Now coming to the top of the stack, E is on top of the stack. Who are all the neighbors of E? B, D, C and F. And our point of concentration is the unvisited neighbors of the current node. So B and D are already visited. So the unvisited neighbors are C and F. Choose one of them and hop to that node and mark it as visited. So I have chosen F. Okay, I have chosen F. As F is visited node, I have sent that to the output saying that it is a visited node, and I have pushed that into the stack also. I have pushed it into the stack also. Now F is on top of the stack. Have a look at this one. So who are all the neighbors of F? D and E are the neighbors of F. Our point of concentration is the unvisited neighbors of F. But unfortunately, both D and E are already visited, right? So as they are visited, there is no option to hop from F. So pop F. You heard it right? Pop F. I have removed F from the stack. Now what is the element which is on top of this stack, which is E, right? Now who are the neighbors of E? Let's make a note of it. So the neighbors are B, C, D and F. The same old funda, look for unvisited neighbors of C. E. B is already visited, D is visited and F is also visited. The only element that is left is C. So make a hop from E to C, right? So make a hop. So as C was an unvisited, now it is a visited one. Give an entry of that into the stack as well as the output, right? So now C is the new visited node as well as on top of the stack. Now our point of concentration is on C. Then who are all the neighbors of C? C neighbors are A and E. Then who are unvisited neighbors of C? Both A and E are visited. So there is no unvisited neighbor of C. So what we have to do? We have to take step 2, pop C from the stack. Remove it from the stack. Once you remove that, what will you have on top? Have a look at this one. If you remove, on the top you are going to have E. Am I right? So who are all the neighbors of E. The neighbors of E are B, C, D, and F. What about the unvisited neighbors of E? B is visited, C is visited, D is visited, F is also visited. There are no unvisited neighbors of E. So can't help it. We need to take the hash step, which is step 2, remove it or pop it. Now on the top you have D. Who are all the neighbors of D? The neighbors are B, E, and F. So unvisited neighbors of D, if you go for B is visited, E is visited, even F is visited. As all these three are visited, again we need to take a hash step, which is to pop D from the stack. I'm going to pop it. Now on top of the stack is B. Who are all the neighbors of B? A, D, and E. Coming to the count of unvisited neighbors, A is visited, D is visited, even E is visited. So there is no unvisited neighbor for B. So I'm taking this hash step of removing it, or step 2, right? Now on top of the stack is A, right? So who are all the neighbors of A? If you look at this one, B and C are the neighbors of A. Unvisited neighbors, B is visited, C is visited. Can't help it. I have to remove, by force, I have to remove A from the stack. If I remove A from the stack, what are the elements that are left in the stack? Nothing. So the top will be given the default value -1, saying that the stack is empty. What do you mean by top is equal to -1? Which says that the stack is an empty stack. The same I have shown it pictorially. So once we remove one by one from the stack, when we reach a condition where the stack is empty, it means that we have visited all the nodes. We have visited all the nodes, and the order in which we have visited them is stored in the output. Okay, this is nothing but your depth first traversal, which is a graph traversal technique which executes with the help of an intermediate data structure, which is a linear data structure, a stack. Right? This is one way of traversal, and a contrary to that is a breadth first traversal technique. This is a traversal technique which uses queues for traversal. Or as I said, moving from one node to the other, visiting all the nodes is nothing but traversal, right? So breadth first search is another traversal technique which we are going to see now. So let's go to the algorithm of the same. Step 1. Visit the adjacent unvisited vertex. That is, choose a vertex from a graph from where you want to start your traversal technique. Mark it as visited, because primarily all the nodes in the graph are unvisited, right? We need to start from one or the other vertex. So if in your exam point of view, if they give you a node as a starting node, you start with that node, or else arbitrarily you can choose any one of the node as the starting node. Okay. So start from a node and mark it as visited. Now, queues are going to help us to perform breadth first traversal. How they are going to help? In case of depth first search, we chose one unvisited neighbor of any node. But here we are going to consider all the unvisited neighbors of a node. Right? You heard me right? We are going to consider all the unvisited neighbors. So I'll insert them into a queue. All the unvisited neighbors, insert them into a queue. Right? If there is no vertex is found, then remove the element from the queue. Now, the primary point. How we are going to insert into a queue and how we are going to delete an element from the queue. Basically, a queue have two ends, a front end and a rear end. From the rear end, we are going to insert the elements, and from the front end, we are going to remove the elements, right? I hope guys you try to recollect the basic funda of a queue which have two ends, which operates at two ends. So one end it is going to use to insert the element, the other it is going to use to remove the elements, right? The front and the rear end. The same terminologies which I am going to use over here. I am going to repeat this process, step 1 and step 2, unless my queue becomes empty. The third step for depth as well as breadth is the same, the concluding point. If the data structure which you are using is empty, job done. Okay, let me help you out by explaining this concept using an example. Okay, so have a look at the example which I have given. The similar one which I have taken for depth first search, I have taken a similar one. Here you can see two arrays. With the graph, with the help of these two arrays, I'm going to perform breadth first traversal. Okay, so the first one is a visited, an array, visited array, right? So this array will have a size equal to the number of nodes in your graph. Say if your graph is having, say that let's make use the terminology nodes. If it is n, then n the size of visited array will be n. Say, right? Along with that, use another array and name it as queue. Children, as I want that my array to behave like a queue, I named it as queue. Okay, even the size of that is going to be equal to n, which is the number of nodes in your graph. Okay, so initially the array visited will be filled with zeros, or you can say false, saying that all the visit nodes in your graph are unvisited right now. I hope you can see. So arrays are you'll have be having the index values 0, 1, 2, 3, 4 and 5. As there are 6 nodes, 0 to 5 will be the index values of each and every node, right? So in place of the index values, I have used the names of the vertices to represent them. That's it. A simple change to what I've made to make you guys understand. Okay. So A to F, right? Let me use this here. And each and every cell of that array is filled with 0, saying that they are not visited. And coming to the second array, which is a queue, which is named as queue, actually is going to behave like my queue only, right? So how an array behaves like a queue? It will have 2 pointers. One is front and the other is rear. Initially, both the front and rear, both of them will be initialized with the default value -1, showing that the queue is primarily empty. Okay, so let's start our job. So the first node which from where I have started is A. So I have marked it as red, saying that yes, A is the node which I have visited. So in the visited array, I made its entry as 1. I've changed it. Or even you can say that false is been converted to true, saying that A is visited. It's true. The statement is true. Okay. As I have visited A, I marked its entry into the queue. Once I mark an entry into the queue, or I have inserted first element into the queue, what will be the positions of the front and rear? Guys, recollect. when we insert an element, the first element into the queue, the positions of the front and rear both will be moved or incremented to the index value 0, right? To the index value 0. So now the front as well as the rear both are pointing to a value 0, right? Now let's come to the second step. Now you think of who are all the neighbors of A. The neighbors of A are B and C, right? So you have to do two intermediate steps in this. That means take it as a subroutine, right? In this step, we have two intermediate steps, sub-steps, which we have to perform. The first one is print the node pointed by front and insert the unvisited neighbors of front. So in the print, basically print is nothing but the output, right? So initially it was empty because we have not visited any node. Now as I have visited A, I am going to print A. Who are all the unvisited neighbors of A, B and C? I am going to mark an entry of them into the queue. Thereby, the position of the rear is going to move to C. It is pointing to C. So you might be thinking, is there any funda saying that you have inserted B and C? Is it any rule? No, my dears, it is not any rule. You can insert C and B. If B is a neighbor of A, in the same manner, even C is also a neighbor of A. There is no priority over here. You can insert C followed by B. You can do that. In a chronological way, I have inserted it. That's it. Okay. Now, the next step will be second sub-step will be remove the element from the front. What is the element that is in the front? A. If you remove it, what the front is going to point to? The front will be pointing to B now, right? The first step is print the node which is pointed by the front, which is A, right? Then insert the unvisited neighbors of the front element, which are B and C. Now remove the element from the front, right? So I'm going to remove A. This is the step if you find unvisited neighbors of the element pointed by the front. So now this is the picture, right? The process continues. Now the front is pointing to B. Am I right? Now my front is pointing to B. So who are all the neighbors of B is my primary point. A, D and E are the neighbors of B. Very good. But my point of concentration is or concern is only with the unvisited neighbors. But A is already a visited one. So I am going to discard it. Okay. So as A is already been visited. Now next point is as I have inserted B and C into the queue, they are already visited, right? So I'm going to change their entries in the visited index as 1 and 1 respectively. Or you can say that we have visited B and C simultaneously and mark it as true. Okay? Yes, come back to our queue session where we're talking about the unvisited neighbors of B. So D and E are the unvisited neighbors of B. Very good. Now what to do? Insert them. Insert them into the queue. D and E. If we insert, what will be the rear doing? It is going to increment itself and it will be pointing to the most recently inserted element, which is E. Once again, I am telling you guys, it is not it is not that B is going to prioritize D or E. It is not going to show any partiality. You can insert E followed by D. You can do that. Okay. So chronological manner, I have inserted D followed by E. Okay. So yeah, this step is done. Then remove the element pointed by the friend. What is the element that friend is pointing to? It is pointing to B. So remove the, then your friend will be pointing to C. Now this is the current position. So once you remove that, what was the primary thing? B must be printed. The element pointed by the friend should be printed, right? So this is the scenario, right? So once we visit B, these are the changes that are going to occur in your breadth first traversal. So let's see it pictorially. Yeah, this is the final picture or semi-final picture. Okay, so this is the scenario. B is also printed. So as D and E have marked their entry into queues, that means they are visited. So I'm changing their values in the visited list as true or overwriting 0 with 1, marking that they have been visited already. Fine? Yes. Let's repeat the same process. What was our condition? Unless the queue becomes empty, we have to repeat this process. Right? Let's go with it. C. Our point of concentration is C. Right? Yes. So, first of all, print C saying that it is visited. Okay, I'll do that. Then, who are all the neighbors of C? A and E are the neighbors of C. Now, our point of concentration is only unvisited neighbors of C. A is already visited, E is already visited. So, is there anything to remove or insert? There is nothing to insert as both are already been visited, right? So, only thing that we can do is remove the element at the front. So, C will be removed and we will be pointing our friend to D now. Okay, these are the changes once we reach C. Have a look. So, no new entry into D. Right? Now, let's have a look at this one. Now, the front element is element D. Who are the neighbors of D, B, E, and F. Then who are the unvisited neighbors of D? B and E are already visited. Only F is the unvisited neighbor of D. Mark an entry of F into the queue. Right? So, print the element pointed by the front D. Remove the element at the front. So, now front is pointing to E. As I have inserted F, my rear will be pointing to F. Right? This is the current scenario. The elements in the output are A, B, C, and D. Front is pointing to E and rear is pointing to F. Good going. Let's see what happens. Next, once you can see that the queue is full, right? Queue is full. The rear has reached its last position. If you talk in the terms of index values, its highest index value it has reached. What is the basic funda in queues? When we call a queue to be full, if the rear is pointing to the highest index value, we say that condition to be a condition which satisfies that queue is full, right? So here we are. Let's see what happens. Okay, as F has marked its entry into the queue, in the visited list, I'm going to make it as 1, saying that F is visited. Right? Now, again, the same story starts. Who are all the neighbors of E? So I can say that B, C, D, and F are the neighbors of E. Then what about the unvisited neighbors? So B entry is already done. C's entry is already done. D and F. Each and every node has been visited. Yes. How we are going to know that B, C, D, and E are already visited? Very simple point. That's why I have used visited array. If the value in visited array for that corresponding node is 1, it is visited 1, right? So that is the basic usage of visited array in our whole breadth first traversal technique. Got it? So E is not having any unvisited neighbors. Sorry to say that. So I'm going to print the element which is pointed by front, which is E. Remove the element at the front, which means that my front will be incremented and be pointing to the last element, which is F. Okay, right. Job done. Next. What is the next step? Right? So don't know unvisited neighbors, both will be pointing to F. This is the current scenario. So guys, can you tell me when will F, that is your front and rear values, will be the same? Guys, think and tell me when F value will be equal to R. A simple question in between. There will be two cases, case 1 and case 2. A case where both F and rear will be holding -1, which says that Q is empty. Or a case where there is only one element left in the queue. So this the case whenever you encounter this in any scenario, your multiple choice questions anywhere, you can please remember this one. The front and rear values will be equal in two cases. First case is when the queue is empty or the queue is bearing only one element. That element position is not defined. It can be an intermediate element, the last element, first element, can be any element. Okay, but only one element is present in the queue. Okay, yes, come back to our breadth-first traversal technique right now. Yes, here we are at F, right? So the front and rear both are pointing to F. Then who are all the neighbors of F? D and E are the neighbors of F. Then who are the unvisited neighbors of F? D is visited as well as E is visited. I'm very, very sorry. No element unvisited neighbor is left for F. I am forced to remove it. So before removing, I have to print the element pointed by the front, which is F. Right? So I have printed it and I'm going to remove it. Once I remove that, what will be the positions of front and rear? As F was the last element in my queue, once I remove it, the queue has become empty and they are going to retain or come back to their original values, which are -1 each. Right? Now we have reached a scenario where, a case where you can see that all the visited nodes are visited. Have a look at the visited array, my dears. All the values are ones. Right? So that means each and every node is visited. Even the queue is empty. All the conditions are favorable conditions. The tides are favorable, right? So all the nodes are visited. And this is the list or the order in which The nodes in the graph are visited when we perform breadth first search. Okay, so this is how we are going to perform breadth first search with the help of queues. Remember guys, depth first search uses stacks, whereas breadth first search uses queues. Okay, these are the two traversal techniques which are used in a graph, right? So we have performed queues, using queues we have performed breadth first traversal. Then the usages of graph traversal techniques, we can use these techniques to get the shortest path, or that will be a major goal in general, to identify whether we can travel or we can touch each and every node in a graph. To know that, we use graph traversal techniques. The best example for graph traversal technique, the usage is traveling salesman problem. Traveling salesman problem is a problem which is been highlighted a few years back, saying that a traversal person is there, a salesman who is supposed to travel each and every city, or town, given to him. A list of towns and cities are given to him. He need to travel, and he wants to travel in such a way that he don't want to touch any city again and again. So he is looking for a shortest path. So in those, to implement those techniques, like getting the shortest path kind of things, we use these traversal techniques. Basically, you might have seen Google Maps, where each and every node is each and every city, town, any prominent place will be represented as a node. You might have seen a symbol, right? So if you give a source to destination, from source to the destination, if I book an Ola cab from our college to my home, then it will show me a number of paths. But if you book a cab, the cab will be showing the nearest path, right? So that each and everything is a graph in this world, right? We know that every problem can be converted into a graph and can be solved, right? So these are the techniques which we generally use in networks. Coming to the computers domain, in networks we use computer networks. So in a network topology, you take any topology like star topology, mesh topology, bus topology, ring topology, you name it. Each and every topology is a graph in itself, right? What a topology tells you, how the nodes, the hubs, the semiconductors, or the gateways, the routers are connected within a network, computer network, right? So that itself is a graph. Whenever data packets are sent from a source to destination, from a source to the destination, they will be looking for a shortest path between a source and a destination. In between, it is going to touch the routers, hubs, it can be, right? So for calculating all these things, these graph traversal techniques are used. As we all know, always the shortest path funda is not feasible. At times, we need to travel in a longer path because the shorter one is under congestion. Okay, in general language, if you say if that route is stopped or is having hurdle of traffic jam, right? So we take another path even if it is longer. So all types of paths. So these traversal techniques are going to help you out in the same. They show you all types of paths which you can adopt. It can be depth first by selecting, by being more choosy, means you are going to select only one neighbor. Out of n neighbors of yours, you are an unvisited one neighbor you are going to choose, or you can have a huge heart and you can visit all your neighbors at once. Okay, so these are the two different traversal techniques that we have, which can be implemented for your traversal techniques in any domain, you name it, in your specific domain, you can use them. Okay. And thank you guys for listening to me patiently. And if you have any queries, please do post me. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.